Welcome to our discussion on evaluation, applications, and spreadsheets. We're going to throw the whole kitchen sink at you today. Okay, evaluation is just a fancy way of saying plug a number in for one of your variables, right? You got X's and Y's and Z's or whatever variables they are, and then they tell you, hey, let X equal 2. And you plug 2 in for X and you simplify, and then all of a sudden you've got kind of a simpler expression or equation. That's all it means to evaluate, right? So we can sit here and we can put a 3 in for A and a 4 in for B, and we get an answer. We could do the same thing for part B. First off, are these going to be the same thing, right? Are A and B going to give us the same answer? And hopefully you're all saying no, because you remember that, all right, with A, part A, right, you're going to square this number, you're going to square this number. But down here, you're going to square their sum, which is different, right? The square of A plus B is different than A squared plus B squared. And we can see that very quickly and very easily, even if we don't remember the algebra, by plugging in the numbers. You plug in the number to part A, you get 9 plus 16, which is 25. You plug the numbers into part B, you get 7 squared, which is 49, which is totally different, right? So those two things do not equal each other for any numbers of A and B other than 0, right? But 0 is kind of, a trivial case. So just remember that A plus B quantity squared does not equal A squared plus B squared. You got to remember you get that little 2AB piece as well. You get 2 times the product of these things. So 2 times A times B. All right, how about an application from the world of genetics? All right, you can read about genetics here. You can read more about genetics here. Basically, we're just going to talk about dominant traits and recessive traits, or dominant genes and recessive genes, and we're going to denote those as a big A for dominant and a little a for recessive. You've got different types of genotypes. You could be a double A dominant, a big A, little a hybrid, which is the same thing as a little a, big A hybrid, right? Or you could be a double A recessive. You can set up, and this is a very common thing to do in biology classes, set up a little square called, I believe it's pronounced a Punnett square, named after the person who kind of invented it. And you just set up, okay, well, parent A has one of each gene, parent B, right, or parent 1 and 2, both have one of each gene. So depending on which gene they kind of give up when they have an offspring, you could get an offspring with a double A, right, a big A, little a little a, big A, or an AA. And whatever these two genes you're talking about, like you talk about eye color, where blue is a recessive color and brown is a dominant eye color, then big A would be brown, little a would be blue, and this would be the only child with blue eyes, right? Because the brown, obviously they have nothing but brown here, but the brown would take over for the recessive blue gene in both of these. So if you had 4 kids, probabilistically, right, it's not guaranteed, but probability tells us that 3 out of the 4 would have brown eyes and 1 would have blue eyes. So, just like we were talking about, suppose a certain population has 2 eye colors, brown and blue. Suppose we have an isolated population in which 70% of the genes in the gene pool are dominant, brown eyes, and the other 30 are recessive. What fraction of the population has each genotype? What percent of the population has each phenotype? Okay, well, if we let P be 0.7 and Q be 0.3, because those are the two probabilities, right? We had a 70% of one gene and a 30% of the other gene. And since P and Q gives us that 100% total, we know that P plus Q has to equal 1. Since P plus Q squared equals all of this stuff, we can find the percents by just plugging them in. P squared, 0.49, so 49% have the double B. The BP and the PB parts, if you add them together, they're going to be 2 times the product, 2 times P and Q. That gives you 42%. And then the QQ, or sorry, the little BB is Q squared, that ends up being 9%. And if you add those all together, that gives you 100%, right? 49, 42, 9, 100. As for the phenotypes, we look only at outward appearances. And since the brown gene is the dominant gene, all three of these gene pairings will have brown eyes. And if you look back on here, that accounts for 91%, right? This plus this is 91%. You're left with 9% are blue. So 9% have blue eyes. All right, so on the spreadsheets. Now, I'm not going to assume that you're using one particular type of spreadsheet. I would imagine most of you will be using either Excel or Google Sheets. I can't imagine many of you will be using Lotus 123 or Quattro Pro, since those are both fairly old, fairly outdated, and very, very seldomly used. But we'll still try to keep our examples as generic as possible, so those of you using any type of spreadsheet can kind of follow along. One of the most important ways of representing variables is as a cell, right? So you think about your new variable as being some sort of manipulation of another cell. So you can think of that cell as a variable. So if you have something in the A1 cell, basically the upper left-hand corner, then over in your A2 cell, you can type some sort of formula that's going to act on whatever value you type into A1, and it'll give you a new output. And then you can have another formula over in some other cell that's going to act on what's happening in A2. So you can have answers that basically react in a chain to whatever initial value you put into them. So it's almost like doing compound functions. Remember doing f of g and g of f in some course? That's what you're doing in spreadsheets. So that's one of the powers of a spreadsheet. It's really one of the greatest things about it. There are many other great things. So now all we have to do is, instead of thinking about our variables as x, y, and z, we can think of them as these cell designations. The other nice thing about spreadsheets is it recognizes all of the basic operations. You can add, subtract, multiply, divide, and raise to powers. Now, this example that we're going to see in this spreadsheet uses pluses at the beginning of every formula to designate that this is a formula. If you're using Google Sheets or Excel, instead of a plus, you would put an equal sign. But just in case you didn't know this, if you actually just typed this syntax, type this exactly what you see into a cell in Excel, it's smart enough to realize that this is you trying to tell it to create a formula, and it will automatically change this to an equal sign, right? It'll turn it into a formula. So it's not so bad that it's listed this way, because it will work in Excel listed this way. And these are just some examples of how you can take a math equation and rewrite it as a spreadsheet equation, right? This is b3 raised to the power of 2. That's your x squared. So now obviously b3 is your x. Then over here you have 2 times b3. So that's 2 times x and then minus 5. And then when you have to have two things divided by 2, you got to put parentheses around it, right? A3 plus A4 divided by 2. And there's no reason why these are, A1, A2 versus A3, A4. We're just showing you different examples, and we're trying to, well, if we were trying to be consistent, these two should have been different from these two, but B3 should have actually been A1, right? Because up here, X was equal to A1. All right, so now you can translate each of these into formulas. Bottom line is, we just want you to be able to put things into spreadsheets and get the right answers out of spreadsheets by using basic formulas. So here's a simple example of something you could do with a spreadsheet. You could start with a beginning balance, and then you can put in debits and deposits, and then get your new balance. Basically something that will give you an up-to-date balance, let's say in a checking account, as you put money in and take money out. And so you would define things this way, right? You start with whatever money is here, and then next month or next operation, right, your balance is going to be D2, which is this thing here, right, minus B3, minus this one, and then plus C3. So it's basically taking the number above it and adding whatever's next to it, subtracting whatever is next to that. Because you can see this one here, this is going to equal D3, which is the number above it, right? Minus B4 and adds C4. So you kind of think of what kind of daily debit or deposit, debit or credit do I have each day, and what's my new balance. So your beginning balance starts at 1,000, and now if you take away 250, you're now down to 750. You add 100, you go up to 850. You take away 300, you're down to 550. And then you can see very quickly, if we start with a different balance of 2,500, but leave everything the same, we can see that everything changes automatically. And I'm sure you're all going, yeah, duh, we've dealt with spreadsheets before. Let's look at another simple example. Look at these numbers here and see if you can figure out the pattern. Right? After you start with the 1 and the 1, where does the 2 come from? Where does the 3 come from? Where does the 5, the 8? There is a pattern to these. In fact, some of you might know the name of it. This is the Fibonacci sequence of numbers. And after you start with 1, 1, each successive number, and in fact, it really does work here too, because this number, every new number is the sum of the two previous numbers. So 1 is the sum of the two previous numbers because there's only one number before it, so you can think of the previous number as not existing. And then 2 is the sum of 1 and 1, 3 is the sum of 2 and 1, 5 is the sum of 3 and 2, and so on, and so on, and so on. Now, you cannot define this second cell as the sum of the two above it because there isn't a cell above it. So if you wanted to define these with a formula, you would have to actually start with just 1 and 1, and then you could define this as the two cells above it. And if you took that formula and then drug it down, it would populate all the rest by using the formula of just add the two above me. And that's the other great thing about spreadsheets is it knows how to do patterns. So for instance, if you wanted to use that idea with something that makes a little bit more sense other than just creating Fibonacci numbers, if you wanted to look at, how much money would I have in an account after a certain amount of time, if you deposit $100 into an account that pays 5% interest compounded yearly, then at the end of the first year, the account would contain $100 plus 5% of $100, which would be $105. At the end of 2 years, the account would contain 105 plus 5% of 105, and that'd be 110.25. So how can you create a formula that does that for you? If you just put $100 in cell A1, how do you make A2 give you this 105? Well, shouldn't it just be A2 is going to equal A1, right, plus 0.05% of A1? You see how you can just swap out 100 for A1, and that's exactly what we would do. And then if you took that formula and drug it down, the next cell would do the same thing to the cell above it, and you could replicate it and figure out how much money and interest you would have in your account at the end of every year for as many years as you want to do it. All right, the last thing we want to talk about is called the what if power of a spreadsheet. And it basically just means we can do these same formulas, but we can also kind of freeze parts of the formula. All right, for our last example, let's say we want to set up something and figure out a balance based on an interest rate. So we could actually plug in our interest rate into B1, put our balance here in B3, and then as the years go up, right, so we can drag, this formula says we're going to start at year 0. This now is going to be A3 plus 1, so it's going to be year 1. And as we drag this down, it's going to become year 2, year 3, year 4, year 5, and so on and so forth. And then this formula is going to say, take B3 and add it to B1 times B3, and that's going to be the new amount. But if we drug that down, the next cell, everything would move down. It would take B4, multiply it by B1 multiply it by B2 times B4, because everything moves down. It's no longer going to multiply by this interest rate. So we need B1 to stay in place. We can't let it change when we change the formulas in our spreadsheet. Well, that's easy to do because all you have to do is put a dollar sign. And in fact, you technically only need to put a dollar sign in front of the 1. So it will freeze the 1, because since you're going to drag this formula just straight down, the B is never going to change. But if you put a dollar sign in front of the B, then the B doesn't change. You put it in front of the 1 doesn't change. If you put it in front of both, nothing changes. And so now you can replicate that formula and get every new year the interest is still based on this 4%. And the reason why this is nice rather than just putting 0.04 in the formula like we did in the previous example is you can now come along and type in a new number up here, and these will all redo right away. And so now you can figure out what would the money be if my interest rate was different. And then of course you can always change your balance and get different numbers that way. All right, that's everything for this video.